Hello, everybody, and welcome to today's web conference. I'm Amber Rhodes from EUCI, and I will be your host today. You have logged into the Lightning and Petroleum Storage Tanks web conference. By now, you should be logged in and seeing the presentation materials on your computer screen. You have the choice of listening via telephone or computer today, so please feel free to choose either option. If you are listening by phone, you will need to mute your computer speakers to prevent any audio feedback. To accomplish this, simply go to the green speaker icon near the upper left corner of your screen. Click on the drop-down arrow and select Mute My Speakers. If you are listening by computer, we do recommend listening to this session via a wired connection instead of a wireless connection to help prevent any occasional interruptions in the audio stream. You also have access to additional audio controls in the meeting room. To mute my voice or the voice of the speaker at any time during today's session, simply go to the green speaker icon near the upper left corner of your screen. Click on the drop-down arrow and select the Mute Conference Audio Only option in that drop-down. In order to hear our voices once again, you will just need to go to the same option and click it again to deselect it. Finally, please note that you may also adjust the speaker volume via this drop-down box as well. If you encounter any technical issues, please use the Tech and Logistical Questions box, which is moved to the lower left corner of your screen. To submit a question, simply type in the lower white area of that box and click the chat bubble next to that box to send your question. Once you submit your question, I'll do my best to help. Throughout today's presentation, you will be able to ask questions of our speaker at any time by typing them in the Content Questions box, which is now on the left side of your screen. After typing your question in that box, you may click the chat bubble next to that box to send. Please feel free to submit questions at any time. We will take questions throughout the presentation as well as during the last few minutes of today's web conference. Please note that any questions we do not cover during today's live event will be answered in a follow-up email. With that, I would like to introduce our speaker for today. We have Joe Lanzoni, who is the Vice President of Operations at Lightning Eliminators and Consultants, Inc. He has more than 18 years of experience in the lightning protection, electrical grounding, and surge protection industries. He has conducted numerous site inspections of industrial and commercial facilities for the purposes of evaluating lightning protection, grounding, and surge protection systems. In the oil and gas industries, these sites have included chemical production plants, refineries, and petroleum storage facilities. With that, I would like to introduce and turn things over to Joe Lanzoni.
Good afternoon, everyone, and welcome to the presentation of Lightning and Petroleum Storage Tanks. And I would like to get started by first just sharing some statistical information with you. Worldwide, there's about 15 to 20 tank fires per year across the globe. And of these 15 to 20 tank fires, about 1/3 of them are related to lightning. In fact, lightning is the leading cause of tank fires. As you can see from this pie chart, lightning accounts for about 31% of all tank fires. This is, as you can see, this 41% refers to tank fires that have an unknown cause. But of all the known causes, lightning is the biggest category. There are some examples of tank fires caused by lightning. As you can see here, I mean, this is by no means an all-inclusive list, but as you can see here, it's not really an uncommon event either. Plus, naturally, since lightning occurs, it's a worldwide phenomenon, naturally you can expect lightning fires to occur all over the world. So in this list, you can see sites in the United States, in China, in South Africa, and Australia. There are some relatively recent tank fires that hit the news. For example, the first one from South Africa in 2007, there was a lightning fire that ignited a 7.5 million liter tank. The fire lasted 57 hours, and damaged about $16 million worth of petroleum and equipment. Here's another example, and quite frankly, in this particular case, the end user was a company named Magellan, and they have since become customers of ours. But they had a tank fire in 2008, and the cost of that tank fire was at least $10 million. And these costs would include the cost of the lost product. Typically, the tank is destroyed by the fire. You also have to factor in firefighting costs and also environmental costs. So often, there are environmental considerations. There may be fines or levies assessed by regulatory agencies as a result of these tank fires. In 1995, there was a very large fire, lightning-related tank fire in Indonesia. 10 tanks were affected, and the plant was shut down for about half a year. So when you lump all of these tank fires together, you can make a few general observations and considerations. Number one, over time, the size of tanks has increased. So older tanks are typically, tend to be shorter, maybe 30 feet high or 40 feet high or whatever, whereas newer tanks might be as high as, 50 feet or 60 feet or whatever. So tanks have gotten bigger over time, just as real estate has become more constrained. Number two, a tank fire is extremely costly. There is no such thing as a cheap tank fire. We have to consider, like I said earlier, property damage, lost product, business operation. Obviously, we're going to have a big public relations disaster to manage for any nearby people and so forth. And then thirdly, controlling tank fires. You obviously, if you have tanks, you need to have firefighting resources stationed nearby. That includes equipment and personnel that are trained to fight this type of fire. Here's some additional statistics on lightning costs. Lloyd's of London says that there has been a 15% increase in lightning-related losses from 2009 to 2010. And according to the National Lightning Safety Institute, lightning-related losses exceeded $5 billion in 2008. In addition, according to some NASA researchers, we can expect a 5% increase in global lightning activity for each 1 degree Celsius increase in global surface temperature. So in other words, as the Earth is warming, we can expect lightning activity to increase. And then lastly, according to the Association of British Insurers, in a few decades, the weather damage during a normal year is likely to be double that of recent history. Here are two local, and when I say local to the United States, two local examples of lightning-initiated tank fires. There were tank fires in Wynwood and Glenpool, Oklahoma, as well as Kansas City and Wynnewood, Oklahoma. I would like to show this YouTube video that was taken at the Wynnewood tank fire in Oklahoma. And again, this is a fully engaged tank fire ignited by lightning in 2007.
Extensive lightning protection system out here, but Mother Nature doesn't always pay attention to that. This is the result. But despite all of this, so far they haven't had to evacuate anybody.
Contractors that are in there doing construction work and stuff like that, we've asked them to leave and things like that. But the essential people that we need to have to operate the refinery and keep systems running are still there.
And right now you are looking at a roadblock. This is on Highway 77. It happens to run right next to the refinery, right next to the storage tank that is currently on fire. It is going to remain closed until they get this fire put out. Reporting live, Kate Godwin, Eyewitness News 5.
It is just a dramatic thing from Wynnewood.
I'm going to try to scoot back to the beginning of the video here so you could see the floating roof tank actually combust.
This was pretty serious. Eyewitness News 5's Kate Godwin is now with us live from Wynnewood. Kate, incredible pictures of the flames themselves. I understand crews there are still at work tonight.
It is not over yet, Tyler. Workers thought they had this fire under control, but about 4 o'clock this afternoon, the flames and smoke started pouring out of that storage tank once again. Earlier today, we happened to have a storm chasing crew in this area. They came by and were here within moments after the lightning struck.
And this is the key frame right here.
The explosion. These tanks have 2 roofs. One is a fixed roof, one is a floating roof. And they think the vapors between the 2 tanks is what is burning right now. They're trying to get some foam underneath the floating roof to get this fire out. The refinery manager tells us that they have an extensive lightning protection system out here, but Mother Nature doesn't always...
Amber, can we go back to the main presentation? So this is a still from that YouTube video, and what we're looking at is the flames being emitted out of the side of the tank. This is actually the roof of the tank being blown off by the ignition. So this is an internal floating roof tank, and the fire was ignited between the outer fixed roof and the internal floating roof, which of course then caused the roof to be blown off the tank. The tank from the previous frame also ignited the tank next to it, and as a result, 2 tanks were ignited in this tank fire. One contained 20,000 barrels of gasoline, and the other contained 50,000 barrels of diesel, and they burned for about 36 hours in total. There was another tank fire in Oklahoma. This was called the Glenpool tank fire, and it occurred in June of 2006. And this was an external floating roof tank containing 125,000 barrels of petroleum. So with those facts and videos and photos in the back of your mind, I would like to next examine the physics behind these tank fires. In other words, how does lightning cause ignition of the tank contents, and what are the physics behind the ignition of these flammable products? So this is a map. Map provided by NASA of lightning strike density, and as you can see, lightning occurs all over the world, of course, and it's mostly in tropical areas. So in the United States, the most lightning active region is the Gulf Coast, stretching from about Houston down through the west coast of Florida. The most lightning active area in the United States is Tampa, Florida, with over 110 days of lightning per year. There's also heavy lightning activity in northern South America, and the most lightning active place in Africa is sub-Saharan Central Africa, country of Nigeria and the neighboring countries here. And the most lightning active area in Asia is Singapore and Malaysia, down around here. So I would like to take a few slides to explain how lightning forms and how it works the way it does. So in a thunderstorm, there is a series of collisions between molecules of air and water and so forth, and these collisions create static electricity within the thundercloud. Basically, it's the same electricity as you get when you rub your feet across a carpet. The friction causes an accumulation of static electricity. In the thundercloud, the negatively charged ions tend to go to the bottom of the cloud, and the positive charge tends to accumulate at the top of the cloud. This negative charge at the bottom of the cloud induces or impresses what's called an electrostatic shadow on the bottom, on the surface of the Earth below the thundercloud. This creates an electrostatic field of between 5 and 30 kV per meter of elevation above the Earth. When the voltage between the cloud and ground reach about 10 to the 8th volts, the insulating qualities of the air begin to break down, and they allow what's called a downward leader or step leader to form. And you could think of the stepward leader as a wire being lowered by the cloud towards the ground. So actually a stream of charge is being lowered from the cloud towards the ground. When this downward leader gets to within a couple hundred meters of the Earth, what's called rising streamers or upward streamers are launched from grounded objects in order to intercept the downward leader. These rising streamers are launched at locations where the charge tends to concentrate, and this would be on the peaks or the corners of buildings, on pointed towers, perhaps out of trees and so forth. You will often have multiple upward streamers being launched in response to every downward leader. The downward leader will continue to progress towards the Earth until it gets to a point called the point of discrimination. And this is essentially the beginning of the last step. So at this location, shown in red here, this is the beginning of the last step to Earth. So in the next step, this downward leader will connect with one of the upward streamers. However, a key point is that it only looks for streamers that are in this hemisphere. So in other words, this downward leader, shown here, may connect with this leader, or this leader, or this leader. It will not connect with leaders over here because it basically doesn't see them as it's moving downward. This is a rare photograph of upward streamers. As you can see here, there were several upward streamers generated by the downward leader. However, the one coming out of the middle of the tree succeeded in capturing the downward leader. And once the leader and streamer connect, then we have the visible lightning strike and all of the resulting secondary effects. As you can see, the upward streamers coming out of this tower and coming out of some of these other trees failed to connect with a downward leader, whereas the leader coming from the middle of the tree successfully captured the lightning strike. So a very common question about lightning is, does lightning go from the clouds to the Earth or from the ground towards the cloud? And the correct answer is both, really, because it starts with a downward leader from the cloud, but that leader is intercepted by an upward streamer coming from the Earth. So there's two components. And when these two components connect, then you get your visible lightning strike, your massive lightning current, and so forth. Speaking of lightning current, how much current is in a lightning strike? Well, worldwide, the average peak current is about 30,000 amps. The 95th percentile of all strikes contain about 80,000 amps. The highest recorded strike, I don't have this on the slide, but the highest recorded strike is in excess of 400,000 amps. Lightning flash will last about 13 milliseconds on average. However, a flash may last as long as, it may last over a second as the current continues to flow between the cloud and the ground. A lightning flash is defined as a complete lightning discharge, and there are often several lightning strikes contained within one lightning flash. And this is what gives lightning its flickering qualities. That's why lightning flickers. Every time lightning flickers, that's a distinct current flow or a distinct lightning strike that is a component of a total lightning flash. There may be up to 30 lightning strikes in one lightning flash. However, the typical lightning flash contains 4 strokes. So on average, it's accurate to say that a typical lightning strike flickers 4 times as it neutralizes the cell between the cloud and the ground. And lastly, the peak temperature of a lightning strike is over 50,000 degrees Fahrenheit. This is, just as a point of reference, the sun is about 10,000 degrees Fahrenheit. So when lightning terminates on a tank here, and this is an illustration of a lightning strike to a floating roof tank, external floating roof tank. As you can see, lightning has terminated on the rim of the tank, the upper rim. Some of the current has traveled down the outside of the tank, and some of the current has traveled down the inside of the tank shell. This current will travel down the insides of the tank shell until it hits the roof, and it will arc over to the roof and spread out across the roof in all directions. So a key point is that lightning doesn't always take the path of least resistance. The correct way to look at it is that lightning takes all paths to ground, and it would be the amount of current is inversely proportional to the resistance of that particular path. So a path with less resistance will have more current traveling through it. However, all paths will be energized to some extent. This is an illustration of a strike to a mast near a floating roof tank. And as you can see, the lightning current travels down the mast and goes in both directions along the surface of the earth. So part of this lightning current will encounter the tank and go up the side of the wall and down the inside and again spread out across the roof. And I would like to just point out that these illustrations can be found in an API standard 545A. So in the standard, we attempt to explain how these lightning current flows across a floating roof tank. So the million-dollar question is, when does lightning flow across the interface between the roof and the shell? See, where a floating roof meets the shell on a floating roof tank, there's a seal, like a rubber seal or a rubber gasket around that roof. And it's extremely difficult to make a perfect seal, especially for in a device or a structure that's so large, like a tank. So there are often vapors accumulating at this seal between the roof and the shell. So when does lightning and when does lightning flow across that roof shell seal or roof shell interface? During a strike to the shell, during a strike to the roof, and during a strike near the tank. So basically, the API has concluded that you will have lightning-related currents flowing across the seal under all circumstances during lightning strike activity. A floating roof tank is most at risk when the roof is high. And the reason is this. When the roof is high, the lightning current will stay concentrated in a smaller area. So in other words, the lightning current is attempting to attach to the roof, come down inside of the shell, and then jump and spread out across the roof here. Well, if the roof is high, the lightning current will be concentrated in a smaller area. If, conversely, the roof is low, then the lightning current has more time to spread out or disperse. And so there is a lower charge concentration when the roof is low. So actually, a tank is more at risk when the roof is high because of the greater charge concentration. Here are here's some other facts that evolved out of API 545 regarding grounding and lightning protection for tanks. So number one, a tank is well grounded if resting on the earth or foundation. So basically, we're saying here that a tank is essentially self-grounded and that no additional grounding electrodes are required for lightning protection. So some owners ground their tanks maybe for other reasons, like for the instrumentation or for the power or whatever. But as far as lightning protection is concerned, a tank is considered to be self-grounded. The occurrence of arcing or sparking or rim fires is not dependent on grounding resistance. So if a tank is well connected to the earth, suppose you have a tank resting on topsoil, which is conductive, versus a tank that's resting on sand, which is highly resistive, these two really do not impact whether or not you might get arcing or rim fires on the roof of the tank. Number three, some owners have a membrane under the tanks, and this would be to prevent any escaped fluids from going into groundwater. And basically, this membrane is, even though it's made of rubber or plastic or neoprene, this membrane does not impact lightning-related currents on the tank. So a membrane neither increases nor decreases the lightning-related risk to that tank. So basically, in conclusion, with grounding, lightning safety is not dependent on tank grounding. A typical lightning strike has three components. There's a fast, intermediate, and slow component in every lightning strike. The fast component lasts up to about 100 microseconds, and the slow component lasts up to about half a second. Here are the three components shown not to scale, but what we're trying to illustrate here is that the peak current occurs in component A. So component A on the left is very brief. In this illustration, it's about 500 microseconds. It's very brief, but it contains the peak current and a negligible amount of charge. The intermediate phase of lightning strike has a lot less current than the component A, but it does contain more charge, about 10 coulombs. Component C, quite frankly, is the most dangerous component of lightning strike. It lasts a very long time. It may not have a lot of current, but it has the most amount of charge or the most amount of energy. So it's typically component C that has enough sustained current that causes fires. I would like to next explore API 545. API 540, I've been a member of API 545 since its inception in 1999. And API 545 is the standard for lightning protection for hydrocarbon storage tanks. It was released in October of 2009 as a RP, or recommended practice. It is probably or likely to become a standard in the future. However, at this point in time, it's still officially a recommended practice. When the committee started meeting in 1999, it became apparent to everyone that we really had to focus on two things. Number one, arcing in the vapor spaces. And what this means is that, hey, we all acknowledge that the roof to seal interface may not be perfect. And so there may be some vapors present at the roof to shell interface. And so if you have arcing or sparking at this location, this can be very, very dangerous and can lead to ignition. Second, we also focused on bonding. Typically, the roof is, as I said earlier, it's surrounded by a seal made of rubber or neoprene or whatever. And this seal essentially insulates the roof from the shell. And so there's various techniques to bond the roof and the shell, because we want to keep the roof and the shell at the same electrical potential during a thunderstorm. Here's a cutaway view of a typical floating roof tank, and you can see the roof and the mechanisms associated with the roof. So, for example, we have the tank shell on the left. There's a shunt, which is a strip of metal connecting the floating roof to the tank shell. And I'm going to talk a lot more about shunts later on. But the shunt is simply a piece of steel that has some spring to it that is bonded to the roof. And so as the roof moves up and down, the shunt will slide up and down against the inside of the tank shell and create an electrical bond between the roof and the shell. There is a secondary seal here, shown here, and then also a primary seal or seal fabric here. And these seals are intended for vapor control. Here is the top of the floating roof, and this mechanism is a hanger assembly, which is kind of like a scissor mechanism that is used to keep the roof centered within the tank. During a lightning event, a typical floating roof has several potential arcing points. There may be arcing at the shunt. So, for example, if there's lightning current injected into the tank shell, there may be arcing at the shunt as the current attempts to go from the shell to the roof. There may be arcing here, and there may be arcing anywhere along this metallic shoe. Basically, if the shell is energized, there's a connection to the roof via the shoe. And so you may have unwanted, undesirable current flows flowing from the shell through the shoe and to the roof. I would also like to point out one more thing about this slide, and this is the statement in green, which says submerged arcing may be okay. So, for example, what I mean by that is, let's suppose this is the top of the floating roof. Let's suppose the level of the petroleum product inside the tank is about right here. Well, if arcing occurred down here below the level of the liquid, then there would be no air present and no oxygen present, and therefore ignition would not occur. So it's okay if the arcing occurs below the surface of the liquid. It is definitely not okay if the arcing occurs above the surface of the liquid. There are two ways or two methods to bond the roof and the shell on a floating roof tank. Number one, a shunt. As I said earlier, a shunt's a piece of steel that has some spring to it, and one end is bolted to the roof, and the other end contacts the shell on the inside of the tank. The second way is to use a bypass conductor. And a bypass conductor, we're simply just talking about a piece of wire that's bonded to the top of the tank rim and to the roof. And this will provide a direct electrical connection or electrical bond between the roof and the shell. Unfortunately, there are several problems with shunts. Number one, the shunt is dependent on the spring tension for contact. So again, a shunt is just a piece of spring steel, and I'll show you some pictures of shunts later. It's just some spring steel that is dependent on the tension in the spring for the contact on the tank. Number two, you could have deposits accumulating on the inside of a tank. So for example, suppose the tank contains crude oil. Well, you may have tar or wax or paraffin or whatever building up or accumulating on the inside of the tank. You may also have, if the tank is not painted, you may also have rust or corrosion on the inside of the tank. Number three, the floating roof is not always centered. So, as I said earlier, suppose you have a very large tank, say 200 feet in diameter. Well, it's extremely difficult to construct this tank in a perfect circle, and it's also typical for this tank to go out of round as it's being used. So as it's being filled and emptied and filled and emptied and heated by the product or heated by the sun, or it may contract at night or in the winter. There's a lot of dynamics going on at the tank. So a tank is typically not perfectly round. And naturally, this means that the floating roof would not always be centered in the tank. Shunts need to be regularly maintained to ensure good contact between the roof and the shell. And number five, they are also a source of arcing as lightning current attempts to travel between the shell and the roof. So here's a photograph of, these are the shunts attached to the edge of a floating roof. And as you can see, this is an unpainted tank, and we have corrosion on the inside of the tank. And so we have shunts rubbing up against a rusty surface, resulting in a poor electrical bond. Conversely, if a customer has painted the tank, then you would have shunts rubbing up against a painted surface. And so again, you do not have a good electrical connection if paint is in the connection. This would be a high resistance connection between the roof and the shell. In this case, the shunt is obviously not making contact with the shell of the tank. Here you can see this photo was taken from the long axis of the tank when it was out of round. As you can see here, the shunt, this thing here, which is being relied on for the electrical bond between the roof and the shell, is simply not making contact with the shell at all. So for decades, the industry has been relying on shunts to provide a low resistance path between the roof in the shell. And quite frankly, this using shunts is not as effective as hoped. The API, when we formed API 545, the API spent over $250,000 to do some directed testing and research to test shunts in real-world lightning conditions. And these tests are described in API 545A. And these tests proved that shunts will arc under all conditions. So previous to these tests, it was believed that if a shunt was new and clean and the surface of the tank was clean and everything was in, new working order, like with clean surfaces and good contact, it was believed these shunts would not arc. And so often tank fires were blamed on these shunts being poorly maintained. Well, as it turned out, a clean shunt on a clean tank surface will arc during lightning conditions. So it really doesn't matter if the shunt's clean or rusty or not. You will still have arcing at the shunt during a lightning event. And this photograph is taken from some of that API testing. This is a shunt contacting a tank wall surface during a simulated lightning event. So another way to bond the tank, shell, and roof is to use a bypass conductor, which again is a piece of wire between the roof and the shell. And although it's a good concept, there are some shortcomings with using a conventional bypass conductor. Number one, it's unnecessarily long. So when the roof, let's suppose you have a tank 50 feet high. Well, that bypass conductor has to be at least 50 feet so that it will remain attached to the roof when the tank is empty. When the tank is filled, then the bypass conductor is longer than it needs to be, and it will just randomly coil and splay on the roof when the tank is full. And keep in mind that the tank is most at risk when the roof is high. So this is an illustration of a tank with a conventional bypass conductor when the tank is full or almost full. You can see here the conductor is just randomly coiled and splayed on the roof when the tank is high, when the roof is high. Another way to bond the roof and the shell using a bypass conductor is to let the ladder substitute as a bonding conductor. So in this case, they are relying on the connection here and here to act as a bond between the roof and the shell. Sometimes owners will also suspend wires along the bottom of the ladder in order to make a bond between the roof and the shell. So let's suppose you have a tank with both shunts and bypass conductors. Which path will the lightning current take? Well, the answer to that question lies on what component of the lightning strike we're dealing with. So for example, the fast component typically travels through the shunts. The slow component will travel through the bypass conductors. So for the fast component, the bypass conductors have too high of impedance to react in time to carry the fast component, and therefore the fast component is forced through the shunts. The slow component is almost DC, so it's considered to be a continuous current, And so since it's almost DC, the bypass conductors will have a lower impedance than the shunts, so most of the current then flows through the bypass conductors. So the current during a lightning strike kind of goes like this. So it starts going through the shunts, transitions from the shunts to the bypass conductors during the intermediate phase, and then concentrates in the bypass conductors for the slow phase. According to the API, the fast component is too fast to ignite vapors, and that the slow component is really the most dangerous component. So vapor ignition, it takes a certain amount of time to ignite these vapors, and the fast component of lightning strike is too brief, whereas vapor ignition tends to occur during the slow component. So if you were to read API 545, you would find that it contains three primary recommendations. Number one, install submerged shunts every 10 feet around the roof. This means that what they're saying is the shunts should be relocated from the top of the roof to under the roof, and that they should be submerged by at least 1 foot. Number two, insulate all seal assembly components from the tank roof. So the idea here is to encourage the lightning currents to travel through the shunts and bypass conductors rather than going through the shoes and the seal assembly and the roof mechanisms. Number three, install bypass conductors every 10 feet around the circumference of the tank. I'm sorry, every 100 feet around the tank circumference. And these bypass conductors should be as short as possible. So I'd like to look at each of these recommendations in a little bit more detail. The first one, install submerged shunts. Well, in order to do this, what you would need to do if you owned a tank would be empty the tank. You'd have to send workers in the tank to remove the shunts from above the roof. You'd have to send workers under the roof to install shunts below the roof. Obviously, this practice would be extremely time-consuming and expensive. If you had an existing tank, what I just described is considered a major overhaul and would be very expensive. And this is the concept. We want to move the shunts from here to here. Number two, insulate all seal assembly components. Again, since we're doing a major overhaul to components below the roof, we need to send workers below the roof, which requires, special breathing apparatus and all that stuff. And again, this is a substantial change from standard designs and would be very expensive for new and existing tanks. And here's the concept. We want to insert insulators between the roof and the shell to prevent lightning currents from arcing from the shell to the roof through the hanger mechanism. Number three, install bypass conductors every 100 feet around the tank. Well, compared to the other two recommendations, this is a relatively easy and inexpensive thing to do. It's fairly easy to retrofit an existing tank with a bypass conductor between the roof and the shell. So a key point from these three recommendations is that the first and second recommendations both represent major design changes, require major overhauls, and can be very expensive. Whereas the third recommendation for bypass conductors is relatively easy to install and can be done immediately and inexpensively, even on an operating tank. So I'd like to focus in on this third recommendation for a minute. this third recommendation, installing bypass conductors, leads us to an examination of bypass conductors. And there's two types of bypass conductors. There's a conventional and a retractable. And a conventional bypass conductor is nothing more than a piece of wire or cable that's connected between the shell and the roof. The other type of bypass conductor is a retractable type of bypass conductor. And this is where you have a spring-loaded reel attached to the top of the rim, and the loose end would be attached to the roof. And so as the roof moves up and down, the spring-loaded cable will deploy and retract as required. So if you were to compare the two types of bypass conductors, if you have a conventional bypass conductor, shown on the left, when the roof is high, obviously the coil will become randomly coiled and splayed on the roof of the tank, as compared to a spring-loaded cable, which will remain as short as possible even when the tank roof is high. For example, let's suppose you owned a 150-foot diameter tank that is 50 feet high. Also, let's assume that the tank is 80% full, which means that the roof is 40 feet high. A conventional bypass conductor would still be 50 feet long in this situation, whereas a retractable cable would only be 10 feet long and be as short and straight as possible. In this case, if you were using one-aught cable in both cases, you would find the retractable cable has about 15% of the impedance of the conventional cable. This is an example of a retractable bypass conductor. This model is manufactured by LEC in Boulder, Colorado, and it's called an RGA, or Retractable Grounding Assembly. And the intent here is to create an electrical bond between the rim, or the top of the shell, and the roof. The loose end of this cable here would be bonded to the roof. So using the RGA is an effective way to bond the roof and the shell. It will also produce the lowest possible impedance connection between the roof and the shell. So it will greatly outperform a conventional cable based on an impedance measurement, and it will also outperform conventional shunts, because since this is a direct bond, would be no arcing or sparking associated with using a bypass conductor, as opposed to the arcing and sparking that you can get when using shunts. So, of the ways to bond the roof and shell on floating roof tanks, we've got several different options. We can put shunts above the seal, like is currently be doing now. Shunts have a high impedance to lightning frequencies and also a high likelihood of arcing. And they're also impaired by the condition of the tank wall. So we could submerge the shunts instead. That's better than having them above the seal. However, now they are submerged, so they're difficult to inspect because they're out of sight. They also have a high impedance, but in theory, if arcs were to occur, these arcs would be under the surface of the earth, under the surface of the liquid where no oxygen is present, and so there would be no risk of ignition. You could also use the walkway or ladder to bond the roof and the shell, and you could use a conventional roof-to-shell bonding cable. However, both of these options do represent high impedances at lightning frequencies. The last option is to use multiple retractable cables. these would have a low impedance during lightning frequencies and therefore reduce the likelihood of arcing at the seal. They're also easy to inspect because they're up at the rim where they're easy to get to, and further, they would not be impaired by the condition of the wall. So, for example, if the wall is rusty or covered with tar or wax, it really doesn't matter because the cable's bypassing the corroded or waxy connections. So, like I said earlier, we manufacture the RGA. Here's what you get if you were to buy one. Here's the spring-loaded cable, and it has a flat braided strap, which is connected to the floating roof using these bonding straps here. Also, several accessories are available, such as replacement strap kits or replaceable cables for the RGAs. To attach an RGA to a tank, you would also need to punch some holes, some mounting holes in the rim and also in the floating roof. Typically, up at the typically when you attach the cable to a floating roof, you can find a flange on the foam dam, which is easy to punch a hole in, and then you could connect the RGA through those holes. So we LEC also can also provide a punch assembly, which is a mechanical punch that can be used to punch the correct size holes in the tank rim or in the floating roof. And this particular punch is certified to not produce arcs or sparks when it's punching a hole. The RGA is ATEX certified. If you're not familiar with ATEX, it stands for explosive atmosphere. So in other words, the RGA is certified to be utilized in an explosive atmosphere. The RGA it's also manufactured in an ISO 9000 environment, and this particular device has received an award for engineering innovation from E&P magazine. I would also like to point out, we're getting close to the end of the presentation, but I would like to point out that there are some fine point notes in API 45 that tank owners may be interested in. Here's the first one. In this section, 4.2.1.2.1, it says in the standard that bypass conductors are used to conduct the intermediate and long duration components. This statement comes directly out of the testing. So like I said earlier, the API spent over $250,000 for directed research and testing. And this testing included injecting lightning currents through simulated shunts. It included injecting currents of different wave shapes to simulate the different components of the lightning strike and so forth. And what they found was that the fast component did not ignite flammable vapors, whereas the slow component did. So it really became obvious that it was critical to provide a safe pathway for the long duration component. The API standard also says that the bypass conductors shall be of the minimum length necessary. So in other words, we want that conductor to be as short as possible. And that favors using a retractable conductor because a retractable cable will always be the shortest length possible. Number 3, these bypass conductors should be spaced every 100 feet around the tank with a minimum of 2. And this is because we want to provide enough conductors to carry lightning current from the shell to the roof, and then also we really don't know where the tank might, we don't know where the strike may terminate. So we don't know if the strike is going to terminate on the north side of the tank or on the south side of the tank or wherever. So we want to have several bypass conductors spread out around the circumference of the tank. 545 shall apply to new or reconstructed tanks. And lastly, 545 says that internal floating roof tanks do not require shunts or bypass conductors. However, it's my opinion that bypass conductors should be installed on all types of floating roof tanks. And you really need to look no further than that YouTube video I showed you earlier. Do you recall that that video showed the ignition of an internal floating roof tank? So I believe that shunts and bypass conductors should be installed on all types of floating roof tanks, although technically the 545 standard is written for external floating roof tanks. So, in summary, the tank fires are not uncommon, and lightning causes about 1/3 of all tank fires. Conventional roof-to-shell shunts and bypass conductors provide a high impedance connection between the roof and the shell. And number 3, the API 545 recommends the installation of bypass conductors. And number 4, retractable bypass conductors provide a low impedance bond between the roof and the shell. I have noticed that a couple of questions have shown up on the side here, so I would like to now address some of these questions. The first question, let's see. We have several small tank batteries consisting of 4 to 8 300 to 400 barrel tanks. Tanks contain either oil or software, in other words, oil field production components. We have halo systems around over the tanks, but there was a strike a few years ago that blew up our tank battery. Is there a better system than the halo system? I'm going to assume that by halo system you mean a wire or series of wires suspended between poles so that the wires are up hanging in the air above the tank. This type of lightning protection system is also called an overhead shield wire or overhead ground wire. It's also called a catenary system. And it's basically overhead shield wires and catenary systems are all basically the same. They are a piece of bare wire that is strung between 2 poles and hangs over the structure you're trying to protect. And this overhead shield wire is then grounded at both ends by ground rods. I think the best way to answer this question would be to ask that you recall one of the very early slides in this presentation. And please bear with me. I'm going to get back to the slide because it's easy to answer this question when you think about this slide. So, if you were to think about this picture here, let's suppose you had a mast. Suppose you had 2 masts, one on either side of this tank, and a wire going between the 2 masts. you would effectively have an overhead shield wire. If there was a lightning strike to the overhead shield wire, that the strike typically terminates near one of the poles holding up the shield wire. So, because the pole is the highest part of that kind of protection system. So, if you have a strike to the pole or to the wire connected to the pole, the lightning current would be split in both directions. So, roughly half would go to one mast and the other half would go to the other mast. That current would travel down the mast, and then part of the current would go this way and part of the current would go this way. The part of the current that goes back towards the tank would travel up the side of the tank, down this side of the tank, and spread out across the roof. If you had a mast on this side, the same thing would happen on this side. Some of the current would go down the mast and then up and across the roof again. So you would have the same net effect of current flow as shown in this illustration. So to answer your question, using overhead shield wires does not prevent current flows across the roof-to-shell interface here. So you will still get current flows across this interface. And so if there are flammable vapors present, you may have ignition occurring even though you have an overhead shield wire and the lightning terminates on that shield wire. So I hope I've answered your question. From that explanation, you could see why in API 545 there is not a recommendation to install an overhead shield wire. We have another question. And the question is, do you ever use other methods of protection, like a DAS in a tank farm, to try and minimize the potential of tanks? So for those of you who may not know what a DAS is a dissipation array system. And the DAS is a type of lightning protection system that is designed to prevent or suppress the formation of upward streamers from the protected area. And so if you were to employ a DAS in a tank farm, you would prevent strikes or suppress upward streamers, which may lead to strikes, from forming in and around the tank farm. So if we were to reduce or eliminate the upward streamers from the tanks or from inside the tank farm, then you would avoid the subsequent current flows that occur from the lightning strike terminations. So to answer your question, yes, the DAS is a viable method of lightning protection. However, it does not subjugate the need to install proper bonding between the roof and the shell. So, I hope I've answered the questions satisfactorily, and I would also like to conclude this presentation and thank you for your attention. And if you have any further questions, you could always get a hold of me at the website and phone number shown on the screen. So thank you for your time and attention, and I look forward to hearing from any of you soon.
All right. Well, thank you very much to Joe Lanzoni, and thank you to our audience for your participation today. An email will be sent to the contact at your site with a follow-up survey asking about your experience today. We do ask that anyone watching this webcast complete the survey, as your feedback is very important to us as it helps us to shape future EUCI offerings. This email will also contain a link to today's presentation materials. I will also be sending another email in about 7 business days to the contact at your site, and the second email will contain a link to the archive recording of today's web conference. That archive will be available for 30 days from that date. If you are new to EUCI and would like to learn more about our other offerings, please visit us at www.euci.com. This will conclude today's web conference. Thanks again to Joe for an informative presentation, and thank you again to our audience for your participation today. The follow-up survey will also appear in your browser window as soon as we close out the meeting room window. I look forward to seeing you at future EUCI events, and we will now close out today's meeting room. Have a great day, and thank you, everyone.